Today we will start with the Nobel Lecture of Irving Langmuir. As you know, that Langmuir is considered to be one of the greatest scientists, and especially he is the one who laid the foundation for surface chemistry. And everything we understand of surface science. Okay? Actually owes it to Langmuir, the very fundamental understanding. Although it is not as if surface phenomena had not been observed before. It had been observed, and there were some extremely important pieces of work which were known, which actually Langmuir mentions about in his Nobel lecture. Which I will just discuss with you now. Now, what is very interesting also is that I was just seeing that Bosch, and we covered the very famous work of Haber and Bosch, and particularly the work of Bosch in BASF. And it's interesting that Bosch and Langmuir got the Nobel Prize in the same year. 1932, and I hope you can understand the phenomenal contributions that they made. I mean, we are talking about the greatest technology that has ever been developed. Forget about developed in 1910 and 20 and 30 ever. There is no greater technology in terms of impact that has been developed so far, which is the nitrogen fixation in the manner that Haber and Bosch did. And again, I mean, if you look at the importance of surface phenomena, and that, we're talking about the person, we're not talking about someone who did some extension work, in the area of surface science. We're talking about the person who laid the foundation. Okay? So those were the kinds of giants, who were recognized in 1932. Now, I mean, I'm not saying that today people don't do great work. I'm sure they do, and there are extremely important pieces of work which continue to be recognized. With various prizes and honors and whatever. But people who are starting a new branch almost, something that I feel is slightly gone down. And so I think that we will need to, and I hope that people like you will have the courage, to really step out and do extraordinary things, like doing it for the first time ever. That kind of thing, one would like to see more of. Okay, and also in areas that are of great importance. Okay, that's also equally important. Okay, so and it's let's see what Langmuir says. During 1932 about the work. At the time, that what was the prior art? What was the status that was known around the time that he really started his research, in industry, and that was around 1900 close to about 1912, 15, around that time. That's when he began his career, after his PhD. Okay, and he says that the phenomenon of adsorption was known well before Langmuir's work. For example, Sir James, of course, this is what I'm writing, for example, Sir James Dewar found that charcoal cooled in liquid air was capable of taking up large quantities of such gases as oxygen and nitrogen. This was known to be a surface action depending on the very fine state of division of the charcoal. Okay. Now, again, I mean, by that time, the Linde air liquefaction had already been invented, and so people actually started doing experiments, where they could cool solids to very, very low temperatures. Okay, so he cooled, charcoal to very low temperatures, and he found that under those conditions, very large amount of gases like oxygen and nitrogen seem to go and sit on the surface. Okay, and but it was also known that it made a lot of difference depending on what was the surface area of the charcoal. Okay, so it looked like that there was an interaction with the surface specifically. So that's why it was not a bulk phenomenon. That's at least what Dewar concluded, and Dewar of the Dewar flask fame. He's the one who did those experiments. Now, what Langmuir also says is that another thing, of course, which was we all knew. I mean, it was always known that soap molecules can lower the surface tension of water. That was known at the time that he began his work. Okay, and most importantly, okay, Gibbs had proposed what we know is his famous equation, which is that if you take dF upon d ln p, where F is the spreading force. Okay, so F is equal to the surface tension of the neat liquid minus the surface tension of the liquid with some dissolved substance. Okay, which lowers the surface tension. Okay, so this would be a positive value. Okay, and ln p is really the partial. P is the partial pressure. Of if I'm looking at gas-solid interactions or gas-liquid, then I'm really talking about the vapor pressure of the partial pressure of the vapor, which is in contact with the surface. Okay, let's say of a liquid. Okay. And or it could even be that if I've got multi-constituents in solution, okay, and they exert osmotic pressure, then I can look at the partial pressure of partial osmotic pressure of a particular constituent, and then basically one is looking at what is the kind of surface excess, of that constituent which one is seeing. Okay, and so that really is measured by sigma, which is the number of molecules which is adsorbed per unit area. Okay, adsorbed on the surface. So that is that. K is your Boltzmann constant, and T is the absolute temperature. Okay, so this equation had already been proposed by Gibbs, but what is very interesting is that Langmuir says that at that time there was no experimental verification of this equation. So it was more in the nature of more like a hypothesis, which had not been proved. Okay, I mean, it was an unverified theory. Okay, which Gibbs had proposed. If let me see, I have seen a more recent day, I think maybe about 8 to 10 years back, someone tried to derive this equation. Let me see if I can find that paper. Then I'll send it across to you. I mean, it's interesting. Now, this is of course Langmuir, and this is in Langmuir's own work. What he says is, prior to 1910, so around that time he got going. Okay, many different theories of adsorption had been proposed, but none of them had been very successful. In most of these theories, the increased concentration of the adsorbed substances near the surface was thought to be analogous to the retention of the Earth's atmosphere by the gravitational attraction of the Earth. So it's very interesting. They're talking about how a local concentration is created like let's say by gravity. And so we know that there is a certain distance over the gravitational effect is predominant. Okay, and beyond that, it gets very low, like the Earth's gravitational field, and in space, you don't see really much of anything. Okay, whereas what we have is up to the upper atmosphere. You know that we do have atmosphere, and of course the atmosphere thins out as one goes further and further away from the surface of the Earth. So there is a particular sphere of influence, of the gravity. So that's what people thought. So what they thought is similarly, the surface also exerts an attraction for molecules, but it is not that that attraction is only at the surface. Okay? That it could spread quite a bit of distance, from the surface. Okay, and I suppose that's what Dewar may have also thought. I mean, of course, they had found that there is a effect of surface area of charcoal, and they knew that surface is important, but they didn't think that it was something that was only so specific to an interaction with the surface. So that's what Langmuir is saying. Okay, an adsorbed gas was thus regarded as a kind of miniature atmosphere extending out a short distance from a solid substance. In general, such theories were called upon to account only for qualitative aspects of the adsorption of gases on solids. Most of the knowledge of adsorption was empirical. Even Gibbs' law had not been verified experimentally. Okay? So that was the state of knowledge. So it is around that time that Langmuir actually got working, okay, on this in this area. But Langmuir came at it in a different way. I don't think he really came wanting to work on surface phenomena. So let me try and tell you, how actually Langmuir got into this area. Okay. And in fact, this is something that I've later on, we'll discuss when we talk about the Ziegler-Natta catalysis and we talk about the work of Ziegler. These are people who, whatever circumstances they are put in, they try to make the best opportunity of that. They don't crave, I wanted to be in this university, look where I am. There's no facilities here. I can't do anything. Those are one group of people. Okay? But there is a tiny fraction who doesn't matter where you put them, they will try to make the best of the opportunity. And so we will discuss that. Okay. So what was that opportunity? Okay. Now, around that time, when he had joined, okay. He was just like Bosch was working in BASF in an industry. Okay, Langmuir had joined General Electric. Okay, and General Electric around 1911, or thereabouts, had commercialized the incandescent light bulb. Which was based on tungsten filament. Okay. Now, here again, it's very interesting, and you will see that basically in 1913, so within 3 years of probably joining the company, 3 to 4 years, Langmuir made a very seminal kind of invention, which really transformed the incandescent light bulb in the sense that the kind of luminosity which one could get had substantially increased, at least by a factor of 2, which was a very, very important finding. Okay. Now, but again, it's always nice to be able to say that what is really the trajectory which was followed in let's say the invention of the incandescent light bulb. Today, it's of course become an obsolete technology. Okay? I mean, it's hard to imagine, okay, that within a century, something that got invented and was considered to be such an important revolutionary thing that you could light up a place, okay, and now it's gone. Okay, this particular technology. Okay, so the first was, 1761. This person actually demonstrated incandescence, and by heating a wire. Okay, today, of course, the phenomenon is better understood. Can anyone say what exactly is the phenomenon of incandescence? What happens when you heat up a body? Well, of course, that is really what black body radiation does. And it was Planck who really later on gave the equation, which explained, how the luminosity varies with frequency, okay, and temperature. Right. Best example is of course our sun, and that it can be treated like a black body radiation, okay, from the surface, and we are talking about temperatures which are extremely high. I think close to about 5,000 degrees or more, okay, and it was that spectral profile which Planck was able to simulate, and later on, of course, people were able to explain many of the things which otherwise were phenomenological. And like you've seen when blacksmiths work, and they heat up these things, and they're trying to kind of bend a pipe or something, and they heat it up and it softens and it bends. And at that time, you also see a reddish glow, okay? But if you're below the temperature, then what happens is it's still radiating, but it will be infrared radiation, which one will get. And as the temperature continuously increases, okay, then what happens is that the brightness increases, and also the maxima of the peak start shifting towards shorter wavelengths. Okay, and that's why we see visible radiation from the sun, because at that particular temperature of the sun, the peak maxima comes really around that kind of a temperature. So that is very well understood. But in those days, of course, that was not known. But the observations had been made that if you can heat up a wire to high temperatures, that it glows. Okay, and that, as we know, is called thermal incandescence. Today, of course, the kinds of light source that you have in terms of LED, etc., those would be different. Okay, but I'm talking about the phenomenon of emitting light purely by the process of heating up an object. Okay, and then these people in 1860, we are talking about. You can see we are talking about 50 years between what 50, 150 years, right? Between the first observation of incandescence and actually the introduction of a incandescent light bulb. Okay, and it was in 1860 that for the first time they were able to take carbonized paper. Of course, carbon will burn in atmosphere, but if you evacuate a glass bulb, and so there's no air and no oxygen, and then you can heat up carbon to very high temperatures, and it also glows. Okay, and also, when we go through some of this, you will understand that Edison, of course, he was a great inventor, but Edison really was always trying to make things practical. It is not really that in all cases Edison was the originator of great ideas. I mean, he wasn't. Like in this particular case, what he did is people had worked on carbonized paper. Now, Edison was smart enough to recognize that a lot of natural substances like banana fiber, bamboo fiber, etc., are all fibers. So he could conceive, of having filaments, and he then was able to carbonize, bamboo, okay, the bamboo fiber, and he was able to demonstrate a very good longevity, of the bulb, and could keep it running for about 1200 hours. And Edison, the other thing was when he did something, he also, tried to make an impact with his invention. So he had that kind of a flair, and so he actually said, "Hey, I'll go and light up the ship," and so he went and put a lot of these things in a ship and actually provided light to the ship, and that was a very, very seminal breakthrough, okay, which he achieved, but close to about 120 years from the time that incandescence had first been observed. Then, in fact, these people, these Hungarians, actually were shifted over to tungsten, okay, from bamboo, and found that they got a much brighter light, than what they could get with the carbon fiber, and also that the tungsten lasted much longer. Okay? So this is also very interesting. I was just thinking that what could have been the motivations? Because tungsten has got one of the highest melting points. We are talking about a temperature of around 3000 degree centigrade, at the temperature at which tungsten will melt. So you can actually keep it, intact for very high temperatures. Today we know that obviously if I take Planck's equation and I put in that value of T, then I can actually estimate, at what kind of frequencies I will get the maxima in the okay, and so obviously I think that really what tungsten did was that it was able to shift the wavelength more and more towards the visible radiation, and also in the process increase the intensity of the radiation, okay, the incandescence. The second reason probably was that see, there will always be things which can go and sit on a surface and contaminate it. But when you are operating at a very high temperature, then those things will probably vaporize from a surface, and the chances that you will always have a cleaner surface, are better. Okay? And I suppose, those were the kinds of concepts, maybe what these Hungarians must have had in their mind, when they worked on tungsten. Okay? And later on, this person who was also working in General Electric, okay, 1906, okay, he is the one who first was able to make a very ductile tungsten, okay, and from which it was extremely easy to make filaments of tungsten. Okay. And once they were able to solve that problem, then actually making the light bulb became relatively easier, okay, and it could be mass produced, okay, and so that's what actually gave the confidence to General Electric to commercialize the the incandescent light bulb, which they did in 1911. Now, obviously, any company or anyone, who actually does something so pathbreaking and revolutionary, they don't actually stop at that. I'm sure the management of GE would have asked a fundamental question, that is it possible to improve the amount of incandescence? Is it possible to make the bulbs glow more? Okay. What is probably they didn't look at it in terms of or maybe they did, that what is the total energy that I'm putting in and what fraction of that is getting converted into light, okay, in the form of incandescence. But certainly, I think that they would have probably put together a team to start looking at the possibility of further increasing the incandescence from the tungsten filament lamp. Okay. And so that's really probably what was assigned to Langmuir, when he joined General Electric. Okay. And now, and Langmuir actually, now there was another very, very interesting development that had happened, okay, then around that time, which again, it was Edison who was, played a pivotal role. Actually, what happened was that, that our own J.C. Bose, Jagadish Chandra Bose, was the person who made the first rectifier for being able to detect radio waves. Okay, and that's what ultimately led to the invention of the radio. Okay, and again, path-breaking invention, and it was Bose. And Bose actually even took a patent in 1901, a US patent on this, which I will show you when I'm covering solar photovoltaic cells, that particular invention. Okay. Now, over here, what happened is, well, before the advent of that, people were still invented in the rectification. And so what Edison had done was something very smart. He realized that there are, which later on we know it was the photoelectric effect was demonstrated by Einstein, but that is for photons impinging on a surface. But also, if you heated up a surface, and this must have been an outcome of the kind of work on incandescence which people did. What was found is that if you heat up a surface, and so I've got let's say a tungsten filament, and then on the other side, suppose I have a plate, okay, and through which I pass, let's say, an AC field, okay, and I connect up the circuit, okay, and what happens is that Edison discovered that you have this process of thermionic emission, which is that electrons get released from the tungsten filament. And what happens is that because I've got an AC field that I have applied on the other side, okay, so if the negative, if I see the negative pole, on the other side, then of course the electrons will get repelled, okay. Whereas when I've got a positive pole, the electrons will get attracted to that pole, okay. So I will generate a current only when in that we are in that particular phase of the AC wave, okay, sinusoidal wave. And so that's what rectification was, and so the first major breakthrough was this rectifiers based on thermionic emission, which was first observed by Edison. Okay, but the problem was that people had found that there is a effect of purity of the surface, and that plays a very critical role in the efficiency of thermionic emission. Okay, and so I think this is from Langmuir's lecture. I'm not very sure where I took it from. A parallel development was thermionic emission. It was first observed by Edison in 1883 as a passage of electricity from a filament to a plate of metal inside an incandescent lamp. In thermionic emission, the heat supplies some electrons with at least the minimal energy, the work function required to overcome the attractive force to holding them in the structure of the metal. And later on, of course, Einstein showed that you can do the same thing, not by heating up, but by actually impinging photons on a surface. Okay, this minimal energy is characteristic of the emitted material and the state of contamination of its surface. Okay, so this is also very important. Okay, tungsten filament was popular, and so these were two major things which a lot of companies were working on. One was incandescent lamp, because I mean that was the first time you brought in a revolution of being able to light up cities. You could light up everything, your room. I mean, and no more a candle lamp. You had a different kind of a source of light. And as I told you, because of the importance of rectification, the thermionic emission also became very important. Okay. Now, what Langmuir does is gives us a background, about how we got into it. When I first began to work in 1909 in an industrial research laboratory, I found that the high vacuum techniques which had been developed in incandescent lamp factories, especially after the introduction of the tungsten filament lamp, was far more advanced than that which had been used in university laboratories. Okay, so universities, even places like MIT and Stanford, etc., which are great universities. I mean, of course, they were working and they had vacuum pumps and things like that. Which there was a lot of high vacuum work that was going on. But Langmuir found that those facilities are nowhere near as good as what industries like General Electric had. Okay, so that's the first thing. And he says that they were far more advanced than that which had been used in university laboratories. This new technique seemed to open up wonderful opportunities for the study of chemical reactions on surfaces and of the physical properties of surfaces under well-defined conditions. Okay, and obviously, because of the phenomenon of incandescence and thermionic emission, naturally, surface phenomenon was important, to the company and to Langmuir. But Langmuir wanted to, of course, improve products, but he wanted to do it in a fundamental way. He did not want to do it in the way of Edison, where Edison, will go and by trial and error come up with, rig up something which is very creative and gives a better effect. Nothing wrong with it, okay? But I think that Langmuir probably preferred a more fundamental approach to solving problems. Now, it's also possible, sometimes it's difficult to make out. What happens is, but it may not be that he first understood all the fundamentals and then went ahead and improved the light bulb. It's possible that he did something clever, just like Edison did so many clever things, okay? And he was able to make the bulb glow better. And then he might have wanted to know, why did that happen? Okay. So the why question could have come later on. Not necessarily that he first asked the why question, got an answer, and then went ahead improving the light bulb, may not have been the case. Okay. Then he says This new technique seemed to open up wonderful opportunities for the study of chemical reactions on surfaces and the physical properties of surfaces under well-defined conditions. I resolved to try the effect of introducing very small quantities of various gases into a highly evacuated bulb containing a tungsten filament. Why? Because you see, Langmuir probably realized that even the best of vacuum means that there will always be some amount of gas molecules which will be present in the environment. And he wanted to know, can that affect the luminosity of the bulb, or can it affect the incandescence of the bulb? Okay. And so and now this is so fundamental. What he says subsequently, since by a McLeod gauge, pressures as low as 10 to the power -8 atmospheres could be measured. So we are talking about 1909. They already knew how to measure a 10 to the power -8 atmosphere vacuum. They had that ability. Okay, but this is the great connect. Could be measured. It was possible to observe the disappearance of an amount of gas of less than 0.1 cubic millimeters measured at atmospheric pressure. Okay. Now, so can one of you quickly do the calculation and show that you get a figure which is close to this? Now, if I take 1 atmosphere of gas, okay, we know that it will occupy 22.4 liters, right? All agree?
Yes. Yes.
Right. Okay. So now, you can suppose I want to now know, therefore, what is there in 10 to the power -8 atmospheres. So what I'll do is that I'll first, I can take 22.4 liters and let's say convert it into millimeter cube. Can you just work it out? How much millimeter cube is that? 22.4 liters.
10 power 6, 22.4 into 10 raised to 6.
Okay. All right. Now you multiply it by 10 to the power -8, which is what the McLeod gauge could measure.
0.22.
Right. Okay. So you can see that it is close to this value, right? Okay. Because this is measured at atmospheric pressure. I mean, that's what he's saying, that it is equivalent to that. And now, Langmuir had that sense that he could also quickly, I think, in his mind, do back of the envelope type of calculations and say, hey, I can actually figure out that if I've got this much of volume, and if one Avogadro number of atoms or molecules is present in 1 atmosphere, then how many atoms or molecules will be present in this? And then he would have also done a quick assessment that if I have got a surface of something, okay, and I know roughly I've got some idea about what might be the kind of distance between atoms in a surface, okay, then I might be able to see like charcoal. Okay, I can try and see what is the spacing between carbons in charcoal. Okay, and then I can see, is there any relationship between these many molecules, for which I can actually establish experimental data and the number of atoms of, let's say, carbon on the surface of a solid. Okay, so so this was the criticality of having a pressure gauge, which could measure 10 to the power minus 8 atmospheres. Okay? And so what he says is, since by a McLeod gauge, pressures as low as 10 to the power minus 8 atmospheres could be measured, it was possible to observe the disappearance of an amount of gas of less than 0.1 cubic millimeters measured at atmospheric pressure. The use of tungsten filament presented particular advantages, for this could be heated in high vacuum to temperatures of over 3000 K, so that all impurities could readily be distilled out of the filament. The ease and accuracy with which any desired temperature could be produced and measured was also important, So that also they had the capability, of being able to control, the temperature. Okay, so they obviously had a temperature gauge, which could go up to something like 3000 degree centigrade. Okay, so now this was again a great example, almost not very different from what we had seen for Ertl or Norman Sutin or Haber, that each of them had some unique equipment which allowed them to do things which nobody else could. Now, in the case of Langmuir, it was a bit different. The equipment actually existed, but probably no one was smart enough to be able to correlate what that vacuum means in terms of the number of molecules that I can see, what is the number of molecules which are typically present on the surface of a solid, okay, and what might be the relationship between those molecules in the gas and those molecules on the surface. Okay, so this is what Langmuir was able to figure out. Okay, and then he says, and you will see that he had a very, very fundamental approach, Langmuir. So he must have been a brilliant student, whose concepts were very clear, okay? And he could do, because these calculations didn't necessarily exist, all of the things, although many of the things that he talks about were already quite well established from kinetic theory. Okay? And so what he says is, when a hot body such as a filament is in contact with a gas of atmospheric pressure in a glass bulb, the convection currents and the uncertain temperature distribution in the gas are factors which greatly complicate any interpretation of observed phenomena involving the interaction of the filament with the gas. So now he was actually interested in seeing the interaction, of the tungsten filament with some gases which is deliberately introducing inside a bulb, to see what their effects are. Okay? Are factors which greatly complicate any interpretation of observed phenomena involving the interaction of the filament with the gas. If the gas, however, is at a pressure as low as 100 baryds, so now this is the unit that they used to use, where 1 baryd, it was typically the CGS unit, so 1 dyne per centimeter squared, which it comes out equal to about 10 to the power minus 6 atmosphere. You can convert it. And so what he's saying is that even if you have a pressure of 10 to the power minus 4 atmosphere, you don't need still higher vacuums. Even at that kind of a pressure, the mean free path of the molecules is many times greater than the diameter of the ordinary tungsten filament. Each molecule which strikes the filament has thus made so many collisions with the bulb since its last collision with the filament that the effective temperature of the gas in contact with the filament may be taken to be the same as that of the bulb. So he says that he was able to get a very good idea about the equilibrated temperature, of the gas molecules, in the bulb. Okay? The disturbing effects of convection currents are then entirely eliminated, and the rate of arrival of gas molecules at the surface of the filament can be calculated according to the laws of the kinetic theory of gases. Okay? So you can see extremely fundamental approach that he took. And then, he says that this is really the equation where mu is the rate of arrival of gas molecules at the surface of the filament. M is the molecular weight of the gas. Okay. Obviously, oxygen molecule is 632, but I could also be looking at oxygen atoms, and that's why he puts oxygen equal to 16. T is the temperature in Kelvin. Okay. And P is the pressure of the evacuated bulb. Okay? That's there, And then what he's saying is, so he knows how exactly to calculate what is the theoretical maximum, of the rate of arrival of gases at the filament. And if, let's say, if there is a reaction between the filament and the gas and it instantaneously disappears, then I know that per second, how many of these molecules would disappear. Right? So he says, by using filaments of small size and bulbs of large size, it was possible to measure experimentally such high rates of disappearance of gas. The disappearance of gas, they also refer to as cleanup. So I introduce a gas inside the bulb, okay, and I measure the change of pressure with time, which tells me how the gas is disappearing, okay, and so that they called as cleanup. Okay? That every molecule that struck the filament disappeared. Theoretically, he said that let's assume, that every molecule that strikes the filament disappears, and I know that that is equal to the rate of arrival of the gas. Then he says, under usual conditions, however, the rates of cleanup were far less than this theoretical maximum. He says he never found this, this instantaneous disappearance. Okay. Then he says the fraction epsilon of all the impinging molecules which reacted on striking the filament could thus be determined. So, he therefore knew, exactly what is the fraction of the gases which struck the filament and actually disappeared because of reaction. So, he had calculated all of this. Okay. And so last time, we discussed that how this tungsten filament was of great importance, whether it was to create incandescent light or whether for electronic emission, and which then became the thermionic emission, which was used in rectifiers. Okay, and so it was very important to know, and from Langmuir's lecture, it's very clear that they were trying to improve the properties, of incandescence. One, and for the electronic emission, there was drastic variation in the efficiency of electron emission, from the tungsten, depending on how this tungsten filament was prepared and fixed. Okay, so obviously there was a great importance to know all of that, and that must be the reason why he conducted these studies. Now, I must also tell you that Langmuir's lecture is very big, the Nobel Lecture, and I am only covering a fraction of it. So what he was basically trying to, I think, understand is things like poisoning of surfaces, which he suspected may be responsible for some of the variation of properties. And so he did a very interesting experiment initially, which probably had not much to do with poisoning, but he just did a fundamental study. And what he did was that he took a evacuated bulb, okay, and into that he injected a certain amount of hydrogen, and we have seen that he used to do his studies with that kind of pressure that even small changes could be detected. Okay, so something like 10 to the power minus 8 bar, which he talked about. So, this was an experiment which he did where he put hydrogen, and he found that basically this is what is cleanup. That is how it is getting removed from the atmosphere, where the bulb atmosphere, and he found that the hydrogen concentration goes down when the filament is heated. Okay, so these were hot heated filaments. Okay, something like I think 1500 Kelvin. That's the temperature at which he heated it, and he found that gradually the hydrogen went down to very very low levels. So then he added some more hydrogen, and he found that again there is some decrease, okay, but clearly not as much as this, probably because he thought that most of the filament would already be occupied by hydrogen, and so he said that that must be the reason why the uptake of hydrogen is has reduced, but it otherwise followed a similar trend that over a period of time the concentration went up. Now, then he did an experiment which looks very obvious later on, but to me, it's always seemed like a absolutely brilliant experiment, And what he did was that he introduced a second filament, okay, and thinking that if the first filament is saturated, then if the second filament has been put, then again more hydrogen should go onto the filament because this filament doesn't have any hydrogen. Okay, so that's the experiment he's describing over here, and that's why I showed you the curve 1 and 2. When a tungsten filament is heated to temperatures of 1500 Kelvin in hydrogen at about 20 bary's pressure, the hydrogen slowly disappears, the pressure decreasing with time as indicated in curve 1 of figure 1. The pressure falls to a very low value in 10 to 20 minutes. If more hydrogen is introduced, the rate of cleanup is somewhat slower, the pressure decreasing according to curve 2, which you have seen. Although analysis shows the residual gas to be pure hydrogen, the cleanup gradually comes to a standstill. Then, this is the breakthrough experiment. With a bulb containing 2 filaments, it is found that the lighting of the second filament does not cause a recovery in the rate of cleanup, which is what he expected. That, if I put in the second filament, he thought that again, it will decline much more steeply. Okay. He says does not cause the recovery in the rate of cleanup. This proves that the gas which disappears is not taken up by the filament itself. This is a remarkable experiment and so simple and very powerful conclusion. So he, we would have all thought that the hydrogen is going on to the filament, but that the second filament did not increase the rate of cleanup showed that it was actually not being taken up by the filament. So what could have happened to the hydrogen in that case? I mean, it's clearly getting taken up because there's a decrease, but it says it's not being taken up by the filament.
Water.
Water?
Sir, it is reacting to form other form of gas.
What else? What else could have happened? Take 5 more seconds.
Hello, sir. Can you hear me?
Yeah.
Sir, the hydrogen may get adsorbed on the inside of the bulb surface. That's why there is no change.
Fantastic. Fantastic. Okay. So, there's no other thing there except for the glass bulb. I've got a filament and I've got a bulb. So if it is not in the filament, then it probably ended up in the bulb. Now, what is interesting is that, but if you did not heat the filament, yeah, then there was no hydrogen uptake. Okay, so you had to heat the filament, and then it ended up in the bulb. So what he says, this proves that the gas which disappears is not taken up by the filament itself. By keeping the bulb in liquid air, a greater total amount of cleanup is obtained. So lower temperatures helped in the extent of cleanup. Such investigations show that the hydrogen which disappears becomes adsorbed on the surface of the bulb, but that the bulb is capable of absorbing only a limited amount of hydrogen. Okay? Because after all, even in the cleanup was gradually coming to an end, right? It was saturating, as far as cleanup is concerned. Okay? This hydrogen adsorbed on the glass is capable of reacting with oxygen at room temperature after the filament has been allowed to cool. Now, this was another very, very important observation. If you just take hydrogen and oxygen, of course, if you ignite them, then of course they'll form water. But if you just leave them, at a low temperature, the hydrogen and oxygen just remain like that. They don't combine and form water. But this hydrogen which was on the glass, seemed to react very, very efficiently with oxygen. Okay. This hydrogen adsorbed on the glass is capable of reacting with oxygen at room temperature after the filament has been allowed to cool. The adsorbed hydrogen is therefore in a chemically very active state. Okay. Conclusion number one. And he's just reaching logical conclusions. Okay. And then he says that it was finally proved that the heated tungsten filament dissociates a small fraction of the incident hydrogen molecules into atoms. Okay. And that these atoms, because of their unsaturated chemical nature, exhibit a strong tendency to be adsorbed on glass. So hydrogen as such will not absorb on glass. And tungsten, without heating, there will be no adsorption of hydrogen on glass. Okay. So the conclusion was the hydrogen first goes to the tungsten. Okay. It gets broken up into probably hydrogen radicals. But those hydrogen radicals don't like to stay on tungsten. So they migrate to the glass surface, the inner glass surface, and eventually, of course, the glass surface will also get saturated. But because the glass overall surface area is much larger than the tungsten filament area, so the amount of hydrogen that gets taken up is much more than what you can imagine based on just the presence of the filament. Okay, so it was finally proved that the heated tungsten filament dissociates a small fraction of the incident hydrogen molecules into atoms, and that these atoms, because of their unsaturated chemical nature, exhibit a strong tendency to be adsorbed on glass. These hydrogen atoms, however, are capable of reacting with one another and forming molecules. From this point of view, it should be impossible to hold on the glass more hydrogen than could form a layer one atom deep. Okay. So what happens is that if these hydrogen radicals, were otherwise, if they're not on the glass surface, if they're just hanging around, then of course they will combine and form hydrogen. And so the only way to account for the fact that the hydrogen cleanup is taking place is that the hydrogen is adsorbed on the glass and is in a very, very different chemical state. That hydrogen does not seem to combine with another hydrogen that easily. Okay, so that was the kind of conclusion that he reached. Okay, and then what he says is by cooling the bulb in liquid air, the adsorption increased. Okay, so definitely lower temperatures increase the extent of adsorption. And then what he says is the maximum amount of hydrogen adsorbed on the glass in these experiments was 0.03 millimeter cube per centimeter squared. I hope you can understand the importance of the first thing that he said, that if he did not have the special equipment, he could not have differentiated that extent of change in the amount of the gas. It was all possible because of this gauge that he had and the very, very high vacuums at which he could operate. Okay, so and 0.03 millimeters cube per centimeter squared measured as molecular hydrogen at atmospheric pressure. Okay, now what is also very interesting, it's always good to do a calculation. Okay, so I just tried to work out. So 0.03 millimeter cube per centimeter squared. Okay, and then you can convert this, let's say, into centimeter cube, which means 0.1 centimeter whole cube, and then divided by, okay, and in 1 mole you'll have 22.4 liters, so it will be 1000 centimeter cube into 22.4. So I'm dividing and multiplied by the Avogadro number, which is for 1 mole of hydrogen. And because there are 2 hydrogen atoms that you'll get from 1 hydrogen molecule, and he has expressed it measured as molecular hydrogen. So I multiplied this by 2 atoms per molecule, and the value comes to 1.5 into 10 to the power 15 atoms of hydrogen per centimeter squared. One of you quickly do the calculation and convince yourself.
So it comes out to be 1.6 into 10 raised to 15.
Okay, that's all right. Maybe I may have made some approximation which was, yeah, but that's great. So you have got 1 point. You can see roughly we are talking about the same value. All right, what he's talking about. So it's always nice, just do a quick sum yourself, and convince yourself that what is being written is right. Okay. Now then he went a step beyond. He didn't just leave it at that. Okay. What he said is this corresponds to sigma is equal to 1.5 into 10 to the power 15 atoms of hydrogen per centimeter squared, which is equal to the number of spheres of diameter 2.8 angstrom, which can be packed per centimeter squared into a close packed hexagonal lattice. So, yesterday I just thought, out of curiosity, let me go and see what is the structure of glass, and on the surface especially, and this was the glass. You can see the red is the silicon, okay, and then I also asked what is the silicon distance, between these. Of course, there is an oxygen bridge, okay, so and it comes out to about 3.05 angstroms, quite similar, okay. Now what happens is, so you can see that if I take a hexagonal close pack, okay, with per centimeter squared of area, what it means is that on average, your diameter will come out to be equal to the effective diameter, okay, will come out to be equal to 2.8 angstrom, okay, of a sphere, okay, and then obviously, he correlated that with glass, and glass at that time, the structure was not that well known, so he just says the spacing of the adsorbed atoms is probably determined by the arrangement of the atoms in the underlying glass, which provide elementary spaces in which atoms can be held. Okay? So that's what he's saying. So it's not very clear exactly where on this the hydrogen goes and sits. But so he just if you take the silicon oxygen silicon length, or the silicon distances, it reasonably matches, with this. So it seems like a good kind of a explanation that that's what is happening. Each of the glass sides, if I take it as a silica, SiO2, actually goes and picks up one hydrogen, and the two are matching very well, which means that we are talking about a monomolecular layer. That's what we are talking about, And the other thing, which of course today we know, at that time I don't think he knew so well. We know that surfaces, like the glass surface, there will always be an incomplete valence, at the surface. There will be unsaturations there, And so that is what motivates the hydrogen from going and binding. Maybe on the oxygen, it will go and form some, there will be a loose silicon oxygen, which is not connected to another silicon, and so there's an unsaturation, the hydrogen goes and binds to that, So that's the kind of thing which likely happens, okay? So 2.8 angstrom, the observed maximum amount of adsorbed hydrogen thus agrees well with that to be expected in a monoatomic film. So what a beautiful calculation and of a monomolecular layer formation. If a glass surface saturated with atomic hydrogen at liquid air, temperature is allowed to warm up to room temperature, part of the hydrogen escapes as molecular hydrogen. The rest can be driven off at 300 degrees C. So, he's also got an understanding of the hydrogen mobility on the surface. Okay. So, at a higher temperature, the hydrogens become mobile. And as he had said, these hydrogens are very reactive. They'll react with each other and hydrogen will come out. But at room temperature or still lower temperatures, the lateral diffusion is very, very less. So they don't see each other, those hydrogens, so they can't combine. So that's what he's saying. Since adsorbed hydrogen atoms probably react on contact to form molecular hydrogen, these experiments indicate that the surface mobility of the atoms is very small at room temperature. So that's what he surmised, So he got so much information from these experiments. Okay. Now, the other very interesting thing that he found out is that when this hydrogen is adsorbed on the glass, these hydrogens can diffuse over long distances through the glass tubing. Okay. And what he was able to do was use that hydrogen, to actually reduce a lot of compounds like tungsten oxide, copper oxide, ferric oxide, all of them got reduced. And he also found that the hydrogen goes and dissolves in platinum. And he knows that because the platinum bulk resistance increased. So, so that was a kind of a proof that the hydrogen is perturbing the bulk properties of the platinum. And it reacts with phosphorus to form phosphine. So absolutely amazing set of experiments. Now then actually came to the crux of it. The problem that they were sensing, for a long time was a problem with, as I told you, for this electronic emission from tungsten, there was a suspicion about oxygen, so he started doing systematic studies with also oxygen films, okay, and so this is about oxygen, not very different from hydrogen, he put some oxygen and there was cleanup and you could see that the oxygen is slowly disappearing. When a tungsten filament is heated to 1500 degree K or more in oxygen at very low pressures, such as 100 baryes, okay, 10 to the power minus 6 atmospheres is what 100 baryes is, or less, the oxygen reacts with the tungsten to form the oxide WO3. But WO3 was known to evaporate readily, and so he says which evaporates from the filament at these temperatures as fast as it is produced, So, it was, the oxygen was coming in and forming, getting activated, forming tungsten oxide, and tungsten oxide was leaving. Okay. And then he uses the word leaving the surface of the filament apparently clean, because, he was measuring the tungsten oxide. Okay. And then he says, at temperatures below about 2200 degree Kelvin, the presence of extremely small amounts of oxygen, 10 to the power minus 6 mm, decreases the electron emission from a tungsten filament to values that range from 10 to the power minus 2 to 10 to the power minus 5 of that from pure tungsten. That was the big problem that they were trying to tackle, okay, depending on the temperature at which the emission is measured. This modification of the properties of the surface must depend upon the presence of a film which contains oxygen. Okay? So what he said is that, look, I mean, the tungsten might be, it's going off. Yeah, I'm forming tungsten oxide, but it looks like there is an underlying surface, where tungsten and oxygen are present at the surface, and probably in a very chemically bound state. Of course, at that time we didn't know that. This modification of the properties of the surface must depend on the presence of a film which contains oxygen. When the filament temperature is high, such as 2000 degree or more, the emission returns to normal tungsten emission as soon as the oxygen is completely consumed or is removed by vaporizing into the bulb a getter such as magnesium. Okay, so what he said is, if I heat it to 2000 degrees centigrade, yeah, it seems to all go, and I'm again restoring the electron emission. But when I'm at about 1500 degrees, not. It's very low. Okay, then what he did was he injected things like magnesium vapor. We know that magnesium vapor will react with oxygen and form magnesium oxide. It's one of the strongest bonds. Okay, and so he introduced the getter, and that was one way in which he was able to kind of remove this so-called extremely strongly bound oxygen. If, however, the filament temperature is as low as 1500 degree, complete removal of oxygen from the gas phase, even by introducing cesium vapor as a getter, does not remove the oxygen film on the tungsten surface after it has once been formed. This means that the oxygen from such a film does not evaporate appreciably at 1500 degree Kelvin. Measurements at higher temperature show that about half of the adsorbed oxygen evaporates at 27 minutes time at 1860 degree. So 2000 it was going off very efficiently. 1860 it took about 27 minutes, and in about 20 seconds at 2000 degree. From the temperature coefficient at this rate of evaporation, it can be concluded that it will take about 3 years at 1500 degree to remove half the film of evaporation, which is the reason why at 1500 degrees, the electron emission was not going up, it was staying that way. Okay, and based on this, and obviously taking advantage of the Arrhenius type of relationships, he was able to estimate what must be the heat of evaporation, and he estimated that it is 160 kilocalorie per gram atom, okay, per mole. Okay, so this is remarkable, that we are talking about an evaporation, heat of evaporation, which actually was more than the heat of fragmentation of oxygen into two oxygen atoms. It's just amazing. So this was the first direct evidence of the formation of chemical bonds on the surface. Okay, this heat of evaporation is far greater than the heat of dissociation of oxygen into atoms. So we have very direct evidence that the forces that hold oxygen to a tungsten surface are comparable to the most powerful chemical forces known. This gives reason for believing that the oxygen film, which so greatly decreases the electron emission from tungsten, consists of a single layer of oxygen atoms which are chemically combined with the underlying tungsten atoms. The electron emission from the tungsten filament in the presence of oxygen at temperatures below 1800 degree is found to be independent of the pressure of oxygen. Beyond a certain pressure, there's no, if you have more oxygen or not, it's not going to take up more, okay, because the filament has got saturated. Okay? So provided, he says, that the pressure is more than 10 to the power minus 3 baryons, there's not going to be any change. Okay, this must mean that the surface is practically completely covered with oxygen, and that an increase in oxygen pressure does not cause the thickness of the layer to increase beyond that of a single layer of atoms. Because remember, in those days there was this theory of gravity. So people did not think that these atoms are only forming a monomolecular layer at the surface. People thought the sphere of influence of the surface extends well beyond the monolayer. But these experiments clearly showed that that's not the case, and that it is really a monomolecular layer of oxygen on the tungsten. Okay, and then in fact, he came to another very, very interesting experiment after this. So what he did was, he had done this experiment. Now he was curious, and he said, hey, what happens if I now inject some hydrogen, into this bulb, and so he started doing experiments introducing hydrogen. Okay, so curve 3 in figure 1 indicates the way in which the pressure of oxygen in the bulb decreases with time when the tungsten filament is maintained at 1500 K. So that is this curve 3. Okay, then he says, in view of the fact that an oxygen film on tungsten at 1500 degree Kelvin does not evaporate in less than a year, it is remarkable that in the presence of hydrogen, the beginning of the hydrogen cleanup curve 5 is so sharp. Okay, so now what is he talking about? Now what he did was that he injected some hydrogen. Okay, and he was just monitoring with time. Okay, and this looks, he found just like this. The oxygen is being taken up. So he reached the conclusion that hydrogen does not interfere with the adsorption of oxygen. Okay, but oxygen interferes with the adsorption of hydrogen. That's what he finally surmised. But let me see what experiment he did. And also, this experiment is one of the best examples I know that exemplifies the need for patience. So he found that it's going down. Okay, and most of us would have stopped the experiment here, somewhere here, and said, oh yeah, there's nothing more to do, stop the experiment. But for whatever reason, Langmuir continued with the experiment. Okay, and suddenly, around 24 minutes, okay, what he found is that, hey, it's all going down again. And this profile was the same as this profile. Okay, which meant that hydrogen now was being taken up. But for whatever reason, there was a long induction period, where nothing seemed to be happening. Okay, so what do you think happened? Take a wild guess. You don't worry about getting it wrong. Now, what basically he said, is that yes, the oxygen is getting adsorbed. But it's not as if at 1500 degrees centigrade or Kelvin that there is no escape of oxygen. There is. And so even if a trace amount of oxygen left the surface, and then it's like a musical chair, the hydrogen says, I have got a place to sit now. Okay? And the hydrogen goes and sits there. And what will the hydrogen do when it goes and sits there? It breaks up into hydrogen radicals. Okay? Now, before it has time to migrate to the glass surface, the hydrogen says, hey, I've got an oxygen right next to me. And this hydrogen in the adsorbed state and the oxygen, which is also in the adsorbed state, seems to react instantaneously. Okay? Once it reacts, then it leaves the surface. When it leaves the surface, it creates more space. More hydrogen gets in, reacts with more oxygen. And like a domino effect, all of the oxygen disappears from the tungsten. I mean, it's just so remarkable and just initiated by that little bit of hydrogen that managed to squeeze itself in on the surface. So what he says is, mixtures of oxygen and hydrogen at low pressures in a bulb containing a tungsten filament behave in an extraordinary manner. Typical results obtained with a filament temperature of 1500 degrees are shown in curves 4 and 5 of figure 1. So this is curve 4 and this is curve 5. These curves were obtained with a mixture of 3 parts of hydrogen and 5 parts of oxygen. When the filament was lighted, the gas disappeared at exactly the same rate as shown in curve 3 when 5 parts of oxygen alone were present. So the first part is very clear. After about 14 minutes, practically all of the oxygen had disappeared. This was confirmed by analysis of the residual gas, which was found to be pure hydrogen. That is, all of the oxygen had been taken out. This hydrogen, however, did not dissociate in the usual way into atoms that disappear by adsorption on the glass walls as shown in curve 1. But the pressure remained practically constant until after about 24 minutes, when the pressure suddenly began to decrease as indicated by curve 5. This curve 5, however, is identical with curve 1, which is characteristic of the cleanup of hydrogen in absence of oxygen. Repeated experiments with different amounts of oxygen and hydrogen proved that hydrogen does not interfere with the cleanup of oxygen. You saw all the oxygen being taken up, but that a minute trace of oxygen of about 10 to the power minus 3 bari completely prevents the dissociation of hydrogen into atoms by tungsten filament at 1500 degree Kelvin. The oxygen thus acts as a catalytic poison. This is the first time, this concept of a catalytic poison, things which poison the surface, was introduced. Experiments of this kind can be used to make quite accurate chemical analysis of mixtures of oxygen and hydrogen. The fact that a monoatomic film of oxygen on tungsten does not react with hydrogen at 1500 degree K is a striking indication that the oxygen is in a condition far different from that of gaseous oxygen. The results, however, confirm our conclusion that the film consists of oxygen atoms which are chemically saturated by the tungsten atoms with which they are in contact. And he has shown that, it forms very stable bonds and the heat of evaporation is 160 kilocalorie per mole. In view of the fact that an oxygen film on tungsten at 1500 K does not evaporate in less than a year, it is remarkable that in the presence of hydrogen, the beginning of the hydrogen cleanup, curve 5, is so sharp. Since curve 5 is exactly like the lower part of curve 1, it appears that once the hydrogen begins to dissociate, the oxygen is suddenly completely removed from the surface. In other words, hydrogen can remove monoatomic oxygen films from the tungsten surface if the atom's amount of oxygen on the surface is less than a definite amount. That definite amount is the saturation monolayer limit. So if I have got less than that, there is some space for the hydrogen to go and sit. This probably means that the adsorbed oxygen molecules cannot react with hydrogen atoms directly, but can react with hydrogen atoms adsorbed in adjacent spaces on the tungsten surface. Okay, and with these experiments, profound conclusions were reached. And let me tell you that although in Langmuir's lecture he doesn't talk about it, but it's very clear to me that what that meant, that even traces of oxygen are going and poisoning the surface, is that what earlier people were trying to do, where they were trying to create evacuated bulbs, with vacuum. Okay, I mean, there would be sufficient amount of oxygen which would still be left, which would deteriorate the performance of electron emission. Okay, and so probably, he came, I think, to these kinds of clever ways of cleaning it up with hydrogen, and maybe after that, he flushed the bulbs, with inert gas. And that probably was also the thing that led to a significant improvement in the incandescence of these filaments, heated filaments, okay, which earlier people were not able to do, probably, because the vacuum was not good enough to prevent some amount of oxygen remaining and then going on binding on the surface. Is that all clear to everyone?
Sir, I have a doubt.
Yeah,
So where does the water that is formed go? Does it?
that's a brilliant question. So, I have not seen, any talk about the water. I suspect that the water, remains in the gas phase under those conditions. I don't know, or whether it goes and binds to the glass surface. Maybe under those temperatures, it doesn't. Okay, but obviously, water molecule, dissociating to radicals is far more difficult, than the oxygen molecule fragmenting or the hydrogen molecule fragmenting. I suspect. Have I answered you?
Yes, sir.
Any other questions?
So it can be like possible that it can either remain in the vapor phase, or it might combine with the tungsten or something like that. The
You mean
water.
the water?
Yes, sir.
Well, if it combined with the tungsten and if it was competing, then it would prevent the hydrogen adsorption. Okay, and so even if it was doing it, it was not doing it to the extent that it prevented the hydrogen from getting adsorbed. In other words, water might have got adsorbed, but it didn't. There was no evidence that it was a poison.
Okay, sir.
Okay. And I suspect that if the water will get adsorbed, the chances that it will get adsorbed on the glass will be much more than its adsorption on the filament. But it's a very good question, unanswered question, and let me just put it down. I really like this. So let me just put, and in fact, one of you had earlier mentioned, and I'll put that also, student, what happens to the water that must have formed? Okay, does it also get adsorbed? And I'm saying maybe, but not to the extent so as to interfere with oxygen cleanup through use of hydrogen. Okay? All clear?
Yes, sir. Is the glass surface considered to be negative? Like, does it have a negative charge?
Well,
I'm
that's a
doubting that
very good question.
because
Today we know that what happens is, that when you have that silicon oxygen, if you don't have a hydrogen, usually the glass, that oxygen, will be negatively charged. Okay?
yes. So then the water can get absorbed on the glass surface maybe because
It
of the
could.
hydrogen present in
It
the water.
could because of the hydrogen bonding.
Yes.
Very good.